Welcome to Professor Russell Esposito's channel on information security. This video is just one of many video modules that are part of Professor Esposito's course on the subject. Video modules for his entire information security course are located on this channel. So remember to hit the like button as well as subscribe if you enjoy the video. Thank you for watching.
So in this chapter, we'll be looking at network fundamentals, local area network topologies, and how data is transmitted, as well as internet transaction and how the protocols are used to bridge a local area network and route data out into another network or to the internet.
These are the four main categories of network topology: star, bus, ring, and a mixed topology as well. Let's take a look at these in a little more detail on the next slide. This graphic illustrates a typical star topology, which is essentially a hub and spoke arrangement. This graphic illustrates a bus topology where cabling has a more linear implementation. This slide shows a ring topology where each device attaches in a sequential manner. An office environment with a few different departments may need a larger network and may use more than one topology at the same time. So for example, an office complex may have a large ring topology that interconnects all of the buildings in the complex. Each building may have a large bus topology to interconnect star topologies located on each floor of the building. This is called a mixed topology or hybrid topology. Now that we've seen how networks and devices may be arranged with different topologies, let's define data communication protocols. Protocols are simply rules for transmitting data. A protocol can define format, compression, error checking methods, and they are sort of the rules of the road and used with the two most dominant networks, namely Ethernet and the Internet Protocol, affectionately called IP. The Open System Interconnection, or OSI, is a model, sometimes called the OSI reference model. It is one of the standards promulgated by the International Organization of Standardization, aka ISO, which you may have heard of. But the OSI model defines worldwide communications, really data communications, by offering a standard framework for implementing protocols and networking components in 7 distinct network layers. The OSI model also provides a certain level of abstraction and isolation for each layer in the model, which each layer in the model only needs to know how to interact with the layer above and below it. As the ancient Chinese proverb advises, a picture is worth 10,000 words. So let's look at a few graphical representations of the OSI model. Here's a nice graphic of the OSI model. The left hand of this graphic illustrates the 7 layers of the OSI model. And to the right, there are descriptions of the Internet protocols that are used in those layers. So for example, if we start at layer 1, the physical layer, that's where the Ethernet cable connections occur. Label 2, which is called the link level, that tracks the actual physical device location, which is its MAC address. Whether you know this or not, every device has a unique MAC address stamped right on it somewhere, including the ISP router that you have in your home. MAC addresses are important for moving data around at the physical cable layer, that part of the network. The next layer up, layer 3, is the network layer, and that's where the Internet Protocol addresses are routed. When you type hofstra.edu, for example, into a browser, it's that 3rd layer in the model that transports your request across the Internet to the right host server. So that's what's happening at layer 3. The 4th layer is the transport layer, and that has to do with how data is delivered. With the TCP protocol, that protocol guarantees delivery, sort of like FedEx or UPS. It has error detection and retransmission features within that protocol. However, the UDP protocol transmission is not a guaranteed delivery. It's faster than TCP, but does not have error detection and retransmission. So UDP is typically used for things like sending data to printers and often for gaming, which does not require the kind of data transmission integrity necessary In other applications, like let's say bank and financial transmissions might, those would use the TCP protocol, which guarantees delivery. And the layers above that, 5, 6, and 7, are the layers that the internet uses to transmit and control the application. So here's where all email occurs, file transmissions, encryption, browser displays would occur, those kinds of things at those top levels of the layer model. Okay, now this slide talks more about MAC addresses and the ARP protocol, which is the address resolution protocol used to identify who has the right MAC address in a transmission. So, as we stated in the prior slide, data and specifically data packets are delivered at the local network level, that is the physical cable level, by means of the device's MAC address. MAC addresses are assigned to a device or its network card by the manufacturer, and each manufacturer is assigned a specific block of MAC addresses to prevent two devices from sharing the same MAC address. Maintaining this list of every local system's MAC address in a network is very cumbersome, time-consuming, and costly. So what happens here is the ARP protocol gets involved, and essentially when a request comes looking for a particular server or host, it sends out first the IP address, and it'll say who owns on the network. This ARP protocol sends out a query to the entire network that every device hears or reads, who is IP address 10.1.1.140 or something like that. And the broadcast query is examined by every system on the local network, but only the system whose IP address is that IP number 10.1.1.140 will respond. And that system sends back a response that says, yes, I'm that IP address, and by the way, my MAC address is 00:07, a lot of colons in the MAC addresses, sends that back. And that's how that's how a transmission at the local level gets to the right physical device by the MAC address. And again, it's really a broadcast that goes out to all of the devices, and the device with the IP address that's being requested will give up and offer up its MAC address so that the communication at the cable level 2 layer of the model can occur. It's important for you to understand this because hackers attack and spoof these ARP tables, and these tables that manage this communication at this low level, at the cable level, and they steal data transmissions, passwords, data, or they could deny services by absorbing all of the transmission, to the attacker's machine. And we'll discuss these kinds of attacks in a later model, but you need to understand MAC and the ARP if you're going to be able to understand the attacks.
In the previous slide, we discussed how the MAC address is used for communication within a network. And the MAC address is stored in the machine, and it's on the network, it's stored in what's called an ARP table. Now, the ARP table is important because it also associates a MAC address with an IP address. So a MAC address is good for a local area network for communicating from machine to machine. But the minute you want to route it to a different network or to the internet, you need an IP address. So the IP addresses are assigned logically to the machines, and they're associated with the MAC address in the ARP table. So the ARP table knows the MAC address of the machine, knows the assigned IP address, and can then use that IP address to route that communication through a router and out to another network, which similarly receives that IP address and then looks for the target IP address and tries to maps that target IP address to the target MAC address. So essentially, each machine has their own MAC address, but to communicate beyond your local area network or through the internet, you need a MAC address associated with an IP address because the IP address is the only number that's routable through a router.
There are many specific ways to create false entries in a machine's ARP cache, and that's what hackers, like to do to take control. The effect is all the same regardless of what the methodology is. Communications will be routed to the attacker's machine. This type of attack is called ARP poisoning. The attacker can use this method to inject himself or herself into the middle of a communication, hijack a session, sniff traffic to obtain passwords or other sensitive data, or block the flow of data, creating a denial of service attack. Although ARP is not secure, packet protections such as IPsec encryption can be used so that the packets are unreadable by the attacker.
Now, this is a slide that lists a number of software ports. These are not hardware port numbers like a physical port in the back of a machine, a router, or a switch. These are software ports that are assigned for certain services over the internet. And I don't want you to memorize all of these. If you're aspiring to take the Security Plus exam, you may have to look at this and obviously practice exams, take practice exams. But the ports you should know are listed on the bottom. Port 80 for HTTP, 443 for secured encrypted HTTPS, and the SMTP port 25 for sending email, and IMAP 143 for receiving mail. Those, I think you should know those. Those are fairly basic. But I think the rest of it I would worry about. We'll talk about the protocol, TCP, UDP, in the center of the chart. One's guaranteed delivery, one's not guaranteed. TCP is guaranteed delivery, so like Federal Express, and UDP is more like junk mail. Think of it that way. But we'll talk more about TCP and UDP in the next few slides in this module. But I wanted you to, I also want you to know, I want you to know what the common ports are, but especially the ones in the bottom of the slide. The rest of the chart I wouldn't worry about. But there are there are thousands of ports that are in use. So I just want you to have an understanding of it without really getting into a conversation that's in depth. So we covered MAC addresses on machines, IP addresses, and the ARP table that associates the MAC number to an IP address for routing out into the internet. But when you think about it, when you go to a website, you're not keying in the IP address. You're looking for a name, Walmart.com, Amazon.com, Bank of America. So there's another table called the DNS, Domain Name Server, and that table has an association of a name, of a URL name like Walmart.com or Bank of New York, Bank of America.com or Farmingdale.edu. And in that DNS table, it has the associated IP address. So you don't have to type in and remember all these numbers. So let's take a further look at DNS.
Let's spend a little bit more time looking at DNS. It has a graphic on DNS and shows how the DNS servers actually work. You see, there isn't really only one server that translates the URL name to the numeric IP address, but rather a hierarchical set of servers that do this sort of work. You may also hear about Dhcp Protocol, the Dynamic Host Configuration Protocol, and it dynamically assigns IP addresses in situations where it may be too cumbersome to manually configure IP addresses for each machine. So ISPs, your internet service provider, they're going to use, all of these providers are going to use DHCP to assign IP addresses for your home computing needs. So you can imagine how challenging it might be for an ISP to manually assign an IP address for hundreds of thousands or maybe millions of homes and keep track of that and track that as people leave the network, the ISP, or maybe come back. So DHCP takes care of that and just automatically assigns numbers, for the ISPs or for the network that's using DHCP. So it's a common protocol. You'll probably hear about it, and it sort of helps you understand how very large networks can be managed with these IP address assignments. Here's another graphical representation of the OSI model. At first, it looks a little busy, but if you look at each layer, you'll see that things will begin to look a little familiar to you in some of the terminology, the protocol names and things. So spend a few minutes looking at this particular slide. Each of the 7 layers are represented here, and they have some small graphics that help describe the kind of activity at each layer. And I've also added to the left, and also within some circles throughout the chart graphic, some of the protocols that we just described. So you have a better understanding of where these protocols do their work within the OSI model. So we've been talking for a bit about IP addresses and how there are 32 bits. So this slide actually goes through it in a little bit more detail. So if you look, for example, at this address 192.168.1.131, look at its binary address. It's 8 bits to a byte, right? I mean, every bit is either an on or off switch in a computer. You're a low voltage or high voltage. That's how everything's obviously processed at a binary level. That's the format for what you're looking at is the format of Internet Protocol version 4. As you can see beneath it, Internet Protocol version 6 has many more bits and bytes and allows for many more addresses to be assigned. And in this version is what the world is adopting for some time now. The next slide will go through some of the benefits of IP version 6. This slide goes through some of the other benefits of IP6. The IPsec protocol has some built-in encryption called IPsec, which you may have seen earlier in an earlier slide. And it also has a simplified header, new addressing scheme. It can be more efficient, has other advantages such as multicasting, and allows for very intensive broadband and multimedia streams of data. So that is where everyone is heading to IP version 6. The topic of subnetting is a bit beyond the scope of the security class, but I just wanted you to be aware of what subnetting is and that there are ways to mask an IP address and create subnets. So subnetting has some benefits and there are some trade-offs. When you subnet, you have some trade-offs between the number of subnets versus the number of host addresses you can have in your subnet. So as you increase your ability to add hosts, you're going to decrease the number of subnets that are available to you. So if you're interested in this topic, there are many online sources and videos to review to gain a deeper understanding of how subnetting works, but it's really sort of beyond the scope of this course. But I do want you to be aware that it exists and have sort of a rudimentary understanding of what subnetting is.
There are two videos here. One defines what a ping command is, what a ping function does, and how it's used for a DDoS, distributed denial of service attack, DDoS. So you'll find these links either in the syllabus or the schedule or on Blackboard.